Let me see. Okay. So last class we started on this plates map. We cut out the pieces. We put the pieces together. We labeled like the longitude and the latitude. And then we created a key to show all the continent names. Actually, I take that back. The plate names, because some of them are just ocean, and some of them include both continent and ocean. And then we numbered each plate, like here's number 6 to represent part of the Pacific plate. Then we drew arrows showing the direction of plate motion, as given on that worksheet. And finally, we plotted the locations of 20 different earthquakes and volcanoes, right? Stars, blue stars for me, I don't know what you used, but blue stars for earthquakes, red stars for volcanoes. So we did a couple of those together in class, and then I asked you to finish on your own. So if you still need to do that, you still need to do that. But what I want to look at specifically right now is where those earthquakes and volcanoes were concentrated. Do we see any kind of pattern related to the earthquakes and volcanoes? Or are they just kind of randomly distributed across the globe?
They're constantly on the tectonic plate lines.
In other words, for the most part, maybe not 100% of the time, for the most part, I agree, Noah, they tend to follow the boundaries of the plates, don't they? Is that another piece of evidence that plate tectonics is a real thing? The fact that these volcanoes and earthquakes usually occur on boundaries is another supportive piece of evidence that is explained by plate tectonics. Now, let's have a look at an even better map showing more than 20 earthquakes and volcanoes. Can you guys see this map now? Let me know. Can you see it?
Yes.
Good. Thank you. So the red crosses are earthquakes. The black triangles are volcanoes, and looks like there's a couple hundred earthquakes and maybe 100 volcanoes that they've shown their locations. And what you'll notice is that they're largely on the boundaries of the plates. Like South America, the boundary is right along this west coast of South America, and then it goes out to here in the Atlantic Ocean. This is all part of the South American plate, and we see volcanoes and earthquakes along the edges of that plate. Next to South America, we have this plate defined by the location of these earthquakes and volcanoes, a small piece of the Pacific Ocean that is called the Nazca Plate. Up in North America, we see the same thing along the edges of the plate. Lots of earthquakes and volcanoes. It extends out here into the Atlantic. We also notice that there are some earthquakes that are not in the edge of the plate. So those might require different explanations. One of the craziest is that, like in Oklahoma, which I don't know if they've marked any of these or not, but lately the numbers of earthquakes have dramatically increased in Oklahoma. They're not huge. They're 3s and 4s and 5s that you can feel, but they're not doing much damage. But the evidence suggests that these are caused by the process of fracking for natural gas. Fracking stands for hydraulic fracturing, where they use fluids, hydraulic fluids, to fracture the rock. Hydraulic fracturing, or fracking, and once the rock is fractured underground, they're able to pump oil out of the rock. So it's a method of getting oil and natural gas out of rock that's in relatively low concentrations, so you can't just make an oil well. Instead, they have to fracture the rock. And it's not actually the process of fracturing that's causing the earthquakes, it's later on that these earthquakes are occurring. So that's kind of a crazy thing, not related to plate tectonics, right? Another really interesting exception to this rule is right here. What's this land right here, you guys? I hope you know. Somebody tell me, what is this right here?
Why?
Yeah, that's Hawaii. And of course, lots of volcanoes and earthquakes there. And it's not like they're connected in a line with the other earthquakes and volcanoes around the edge of the Pacific plate. Instead, it's in the very middle of this plate. And so this calls for another explanation. And so I want to take a couple of minutes to talk about Hawaii. And, oh wait, Marvin, you got here. Yeah, let's be on time, okay? But thank you for being here. I want to talk about the Hawaiian volcanoes for a minute. I apologize for not setting up a field trip, if you get my drift, my continental drift there. But the Hawaiian volcanoes are an exception to the rule that volcanoes and earthquakes occur along the edges of plates. So can we explain the presence of these volcanoes and still hold on to the theory of plate tectonics, which says volcanoes and earthquakes should occur at the edge? Well, to begin with, I think we should have a look at some videos. Since I can't take you on a field trip there, at least we can look at some video of some of these Hawaiian volcanoes. How'd you like to do that little excursion? Watch the lava dripping into the sea, forming all that steam.
That'd be pretty cool.
Yeah, so this is a type of volcanic eruption. We're going to learn about different types of volcanic eruptions. Here we are in Kilauea, which is part of Hawaiian Volcanoes National Park. It's the most active of the volcanoes, and it's been erupting for something like 20 years constantly. It's been going off, but most of it is this very liquidy lava that flows along without exploding. I think that there is not very much gas in this lava, so it's pretty safe to be close to it. Of course, if you stepped in that, it would immediately burn right through your shoe and your foot. That lava lake. And sometimes it's quite actively churning around. Here they've moved the lava flow to make this road. They bulldozed it, but you can see where the lava was on the sides. So this makes this kind of, look at that stuff boil away. This makes this kind of lava that actually has a name. There's two different names that we use the Hawaiian names for this type of lava. This lava that's, they call it thick and ropey because when it hardens, it looks like a bunch of ropes lying next to each other. And that's called pahoihoi. That is the geologic name for this type of lava, pahoihoi, that forms that style. And then there's another Hawaiian name that geologists have adopted for another type of lava, and it breaks into these very sharp, angular pieces, and it's called a'a. So this is a Hawaiian word for that type of lava. I figure a'a must be because it hurts their feet when they walk on it. Just a little more. Look at this. How would you like it if this was your house, or this was your house? There is nothing that can stop this lava. It's moving slowly. You could stand right here. Here's the photography, but look at it creep along the street. But you can't stop it. You might have time to get your most valuable possessions out, but it looks like you're going to say goodbye to that car. So it's an unstoppable force once it starts to head in your direction, but it is not explosive in this location. So you can see this is glowing. That's hot. So let's go back to the PowerPoint and figure out what's going on with these. Oops, that's the wrong one. What is going on with these Hawaiian volcanoes? Why are they in the middle of a plate where we would not really expect them to be found? So are you guys on the PowerPoint with me now? Somebody let me know.
Yeah.
Anybody there?
Yeah. We're on it. Yeah.
Somebody tell me. Oh, I turned the sound down. Maybe. Sorry. Go ahead. Tell me again.
Yeah.
Okay, thanks. Sorry about that. I had the sound turned off on the video. So what's going on with these Hawaiian volcanoes? Well, let's start again by reminding us, we're asking this question, why are there volcanoes that are not on the edges of plates? Let's start by looking at a map showing the volcanoes in Hawaii. All the islands have volcanoes, and then there are some that are also either forming tiny islands like Kaho'olawe, or this one down here, Loihi. Now Loihi is active. Loihi and Kilauea are currently erupting. None of the other ones are active. It's only these two. Loihi has not broken the surface of the ocean yet. It's an underwater volcano where lava is coming up from the sea floor and building up a volcano little by little. It's getting taller and taller year by year. We think that in the future, and it might be, I don't know, it might be 10 years, it might be 1,000. We think in the future, Loihi is going to break through the surface and be the newest Hawaiian island. So it's interesting that only these two, Kilauea and Loihi, are actually active. Mauna Loa, that one might be active too. But notice they kind of form a line, and it's at the end of the line that we find the active volcanoes. This is a clue to what's going on. So perhaps our next step should be trying to find out the ages of all these volcanoes and all these islands. When we measure the ages, this is what we find. Look at those numbers. I'm hoping you notice a pattern. Do you see that the oldest Hawaiian island, Kauai, is basically 5 million years old? Oahu, 3 million years old. Molokai, not quite 2 million. Maui, just over 1 million. And the big island of Hawaii, the place that has the active volcanoes still, is not even 1 million yet, not even 500,000 yet. So we did this by using our radioactive dating techniques to find out how old these rocks are. And we find this very steady pattern showing that the islands are oldest in the northeast and youngest, in the northwest, and youngest in the southeast. And then we also have this new one forming on the sea floor. Incidentally, if you measure from the bottom of the mountain to the top of the mountain, the island of Hawaii is actually the biggest mountain on Earth. It doesn't go up in the sky as high as Mount Everest, but from bottom to top, it is taller because Everest starts on a plateau. So it kind of has a head start in terms of reaching higher into the sky. But from bottom to top, this is our biggest mountain.
So the islands are moving towards the lower 48.
Okay, so we think, yes, they are moving. I would modify your direction that you're thinking about. Remember, this is the oldest, and this is the youngest over here. The lower 48 would be over here.
Yeah, but I mean like towards the right. As far as their actual direction, it's more towards Mexico.
Okay, we're going to look at that. Basically, what we think is happening is right here is what we call a hotspot. Let's circle these active volcanoes, first of all, Kilauea and Loihi, keep that in mind. And we think that there is a spot in the magma, in the mantle, where magma is rising here. And that's why these islands are forming. But these ones are no longer active volcanoes. These are dormant volcanoes or even extinct volcanoes. We don't think that they're going to activate ever again. A dormant volcano is one that has not been active for some time, but has the potential of erupting again, like Mount Rainier in Washington State. But these ones we think are completely extinct. And that's because we think there is a hot spot in the mantle where magma is rising up. So here's our hot spot. The magma is rising up on the island of Hawaii right now. And notice that we have the ages of these, and there's some variation, but they pretty much still have that same pattern, oldest, youngest. What we think happened, Kauai was the first of these that was formed, and we think that once the plate was sitting over the hot spot here. And then Kauai, as the plate moved to the left, to the northwest, as it moved in this direction, Kauai got dragged off of the hot spot, and then the hot spot formed Oahu. So for a while, it was just these two. And then they got dragged along after a couple more million years, forming Molokai. And then it got dragged away, and Maui grew up. And then they all got dragged further away from the hotspot. And right now, part of the island of Hawaii is sitting over it. And we think in the future it'll get dragged away, and Loihi will be the only one over the hotspot. Here's another view with our measurements of their ages again. Here's our hotspot forming the current Hawaii, Maui. Oh, I guess that's Molokai, Oahu, Kauai. But look, those mountains don't stop with the last of the Hawaiian Islands, Kauai. They keep going. But most of these ones, now think about this, wouldn't these guys be older if they were formed over that hotspot too? Wouldn't these mountains all be older than Kauai? Which means there's been more time for them to get eroded away. So we think most of these, which we call seamounts, are not sticking up above the ocean anymore because they got eroded. Some of them do stick up above the sea, like the Midway Islands. Here's another view of this. Here's the Hawaiian Islands. Then we have a chain of seamounts going in the same direction. Actually, we have two chains, one called the Hawaiian Ridge and another called the Emperor Seamount. And this brings us to another interesting observation. Check out how it changed direction here. Basically, if we went to this very oldest, oh, how old are these? There we go. Do they follow the pattern of ages? 59, 56, 55, 55, 48, 43, 42, 27, 20, 19, 12, 10. And then we saw these guys, 5, 3, 2, 1, less than 1, and still forming today. So these guys all follow that same pattern of ages. And they form this nice straight line showing that the plate has been moving in this direction, carrying them to the northwest, except for these guys. They're going straight north. So what we think happened, here's the oldest one. We think this used to be over the hotspot, right there. And it got carried north. And the plate was moving north for millions of years. How many million? We think it was moving in that direction from 59 to 48, about 10 million years it was moving in that direction, moving north. So this oldest one here was formed here. It got carried north for 10 million years, but then for some reason that we would want to investigate, the plate changed direction. Instead of going north, it started moving northwest. For the next 40 million years, any volcano formed over the hotspot was carried to the northwest. So we have this line of these two seamounts that we think are explained by plate tectonics, where we have an unmoving hotspot, and as the plate slides over the hotspot, a new volcano is formed, and then it gets dragged away, and that volcano goes extinct, and eventually it erodes down to just being a seamount. Meanwhile, a new volcano is forming over that hotspot. And it recorded the direction of movement and a change in that direction. Gives us this big question of why. You might also wonder, what next? Well, look where these guys are headed. They're headed for the edge of the plate. And this is where subduction is occurring. So we think that these seamounts are going to get carried into this trench and get carried underneath these other continents. Here's the edge of the Eurasian continent. Here's the edge of the North American continent. We think they're going to get dragged down into the mantle and melted and destroyed completely in the distant future. Crazy stuff. Okay, so let's see, where are we? We are here. I would like you, first of all, if you have any questions, please let me know. All right, so here's the worksheet. And we already did 1, 2, 3, and 4. If you fell behind on these, just double check to make sure you've got all of this taken care of. Here's the numbering of the plates. Here's the arrows showing their motion. Here's the volcanoes and earthquakes, right? And then there are a series of questions for you to answer. And so this is what you're going to spend most of the period working on. In a minute, I'm going to end the meeting and allow you to spend the rest of your time, class time, working on this, and then turn it in so you can get your points. Also, I really want to make clear that I accept late work. There's only a 10% penalty if you turn it in late. So if you earned a B on an assignment but turned it in late, you end up with a C, but that's way better than a 0, right? But before we do that, I would like you to go to Teams, and I would like you to go to your class notebook. In your class notebook at this point, you should have 3 sections, 3 chapters. Let's just make sure we're all in the same place for the class notebook. So go to the class notebook in Teams. Some people like to open it up in OneNote. I've found that OneNote has a little more power than the Teams version, but you also have to sign into it separately. And for now, all we're going to do is catch up on setting up our chapter 3 if you haven't done that already.
What would the name be?
Sorry?
What would the name be for the section?
It's going to be Unit 3, Plate Tectonics. So each section should have a number, a unit number, and a name. So I'm going to have a look at how we're doing here. It just takes a minute to get this whole thing running, right? So looking at this class, still loading. We should have 3 sections. Our first section is Intro to Earth Sci. That should say Unit 1, Intro to Earth Sci. If you need to change the name, just right-click on it and click Rename. Then you should have Unit 2, Earth's Interior, Unit 3, Plate Tectonics. Okay, I'm going to call you out one at a time. Let's see, Jessica, the only thing I see you need is, it would be nice if you added the phrase Unit 1 to the first section, Intro to Earth Sci. Gabe, yours is looking good. I see all 3 sections there. Same for Marisol. Rose, I would add Unit 1, Intro to Earth Sci. Oops, wait a minute. You just added Unit 1 to Unit 2. So these 2 units are out of order. The other thing you can do is drag them into the correct order. So Earth's Interior should be Unit 2, intro to earth size should be unit 1. So ideally your units are listed in order and they are also named as well as numbered. Let's see, Marvin, yours are good. Again, you might want to add unit 1 to the title of that first section. And Noah, yours look good. You have all the unit numbers and all the names. Okay, the next thing I would like you to do is update the table of contents for unit 3, plate tectonics. So you should start off with page 00, table of contents, and then we're going to add those contents one by one, and I'm going to put that on the screen for you now. In the future, I'd like you to be able to do this yourself. So you should see I have 5 pages in the table of contents so far, right? And these are the things that you will need to insert into your class notebook, right? Now, I've also learned that in Teams, when I ask you to upload an assignment when you finish it, that's great because it gives me a notification that you did it. However, I can't really score it right there in the assignments section. So I would ask you, when you finish an assignment, do 2 things at the same time. And you have to do these 2 things anyway. The only thing I'm asking you to do differently is to upload it to the notebook right away when it's done. Go ahead and upload it to the assignment, and that gives me a notification that you did it. But if you upload it to the notebook, then I can score it in the notebook, and it's right there for you with all my comments and stuff. So as soon as you finish something, I want you to turn it in 2 different ways. In the assignments section, which gives me a notice that you did it, and in the notebook where I can score it. Unfortunately, the notebook does not give me a notice when you update it. So that's why we have to do it in 2 different ways. And we were doing that anyway. I'm just asking you to do them immediately when you finish an assignment. So at this point, you should be updating your plate tectonics table of contents to include those 5 pages.